and thanks for the very nice introduction. I see that you've done lots of research. You should have asked me, I could have given you a shorter narrative. So yeah, and I would like to thank the organizers for setting up this nice workshop, and it was very easy for me to accept, to come here to talk. What was slightly harder was actually to decide what I want to talk about, right? I really like this program, this multi-fidelity, multi-level, let's say, hierarchical approximations in this context for uncertain problems, and eventually I decided on this quite long title and topic, but the reason I was hesitating what the title was or the topic was that the results are actually not that new. The results are rather old, so I was hesitating, hey, maybe I want to present some new results. At the end, I decided to stick to these type of results for two reasons. I think they fit very nicely to the workshop, so that was very important to me. But secondly, although the results are not that novel, I think they're still, of course I'm very biased, I still think they're quite interesting in the sense that we're working slightly outside this usual multi-level thinking. And I want to use this as a way of stimulating thought, maybe for some of you who work on multi-level methods, to get an idea how creativity can sometimes lead to something that provides what I would call a more comprehensive way of quantifying uncertainties. Okay, so this workshop is about multi-level techniques, multi-fidelity. I think is the word that's used in the title. It's not necessarily uncertainty quantification. I would argue uncertainty quantification has vastly benefited from these hierarchical approximations, in particular for computation models. And although I don't need to motivate uncertainty quantification, I still like to show this slide nonetheless because it has some nice pictures of applications where we have used the tools that I'm just going to present. Okay, so we have some applications in aerodynamic design and uncertainty, or some contact mechanics of some nonlinear models that are relevant. And what I guess most of you agree on is that these mathematical models that we use to describe something in the real world, they are, well, they're very good oftentimes, but they are far from perfect in the sense that there may be uncertainties and there may be a lack of knowledge. And that's my view on uncertainty quantification, which is important to me, that I always want to highlight. It has these two kind of complementary directions. And we have seen fantastic talks this week already that have described fantastic ideas on this lower branch. So at the core is always this model, and by the lower branch I mean, the upper branch I want to describe first, So we always have this model in the center, which is our, let's say, model to describe physics. And the upper branch is what I call inverse uncertainty quantification. How do I get data, observations into the model? Or let's rephrase, how do I actually know what's the uncertainties, what is the distribution of uncertainties that go into my model? And we have seen this inverse problem setting in some talks. What I want to focus on today is this lower branch. So it's just a simple idea of how do uncertainties are being forward propagated through the model. But for me, that's why I put this on the slide explicitly, it's important, we really have to think both ways for applications, right? Both are really important. Okay, as I already said, uncertainty quantification for me has these two branches. We are focusing on the forward part, and I will be talking about multi-level ideas, okay? And I will spend a few minutes, hopefully not too long, on introducing what I believe most of you know, namely the basics on Monte Carlo and multi-level Monte Carlo. And then I will sketch some extensions to go beyond their applicability to something that goes beyond expected value. Okay, so I feel a little bit embarrassed to show you the simple slide because I mean, many of you are working precisely on this, but just to introduce notation, as I said, we have our model, it has some random input, it goes into the model, and we use the model to compute some quantity of interest. Okay, so what we're interested in then is this kind of quantity of interest, is, let's say in the easiest case, if this was to be a scalar, it's a random variable, so we have this mapping from a certain distribution on our input side to a certain distribution on our quantity of interest. Okay, and then what I mean by uncertainty quantification is really saying forward uncertainty quantification. We want to understand some statistical quantities of this quantity of interest, and we want to do this for a class of problems as generic as possible, so under minimal regularity assumptions. If you can prove certain regularity assumptions, like in the talk from yesterday evening. We have seen some ideas on how we can get better or more efficient methods than Monte Carlo. Here we're saying, hey, we don't have this regularity. We don't know whether we have it. Okay, but of course this is not exactly what we're doing. So in practice we have to replace our model by some computational model. So we're introducing some approximation error. That's why I'm using this little letter H. So you know it's an approximation error, and hence also the distributional of my quantity of interest has slightly changed. And then the whole idea is I have to account for that, and the kind of the workhorse of VQ or has always been this Monte Carlo method. So this is what I call a general purpose method. And again here, just to set the scene and the notation, what I mean by Monte Carlo is we take a sample of n realizations from this input distribution. For each sample, we compute our quantity of interest, and then we use the sample average as an approximation to the, say, the expected value. So we are committing two crimes, so to say. The first one is we want to estimate the expected value of Q. We approximate this by the expectation of our computable quantity of interest. And then we're doing the sample average. And of course the question is, how do we combine both error terms? So how should we choose the number of samples n, so the number of input realizations, and how we should then select h, or discretization parameter, such that we get a good result at acceptable or best, ideally at minimal cost. So we quantify this through some criterion, what do we mean by accuracy, and what's simple, and what I will stick to the talk here is the so-called mean squared error. So I'm looking into, wrong button, there we are. So I'm looking into the expected squared distance to the true value, so between my estimate and expectation. Since the samples are all independent identically distributed, I get that this error splits into a squared bias and a variance contribution, so a term that is exclusively controlled by some discretization coming from our computational model, and some term that is quantified by statistical error from sampling. And of course we want to balance both terms by controlling the first term, let's say to be below a certain threshold tolerance squared, or epsilon squared is what I'm going to use. I can decide a way of selecting h, and then here I can then in the second step decide a certain number of samples to match that error. Overall, this goes to this complexity analysis. It's always this idea of balance, how much cost do I have invest to gain or to guarantee a certain accuracy. And so the running assumption is that we have a certain control over how quickly this bias decays as a function of the discretization parameter. We assume that our variance is bounded for sufficiently small discretization parameters, and that the cost is somewhat, to generate one of those samples, is inverse proportional to the discretization parameter. And then in order to achieve a mean squared error that is bounded by epsilon squared, I get to this cost. Okay, good. This is standard, been around for ages. That's our baseline. We want to improve upon that. Okay? And under minimal assumptions, so we're going to have to refine assumptions, but we want to be careful about that. And of course, you can also in practice, it's quite often of interest to look into different error criteria, not just mean squared error, but something like engineers like to look into a probability of failure. So you want to minimize a certain, ensure that the probability of failure is not too large, hence you want to find h and n such that a certain probability is met. This is on first glance is a bit more tricky, because so this guy here, my estimate is a random variable, but I don't know its distribution. But then of course it's a Monte Carlo method, and we can use standard limit theorem to at least get a good proxy. Okay, so that's what people use in practice. Okay, I'm rushing through this a little bit because, as I said, I think that's what most of you have seen multiple times before. And now I also introduce my notation for multilevel Monte Carlo, which is the, let's say, an idea of introducing control variates as variance reduction to Monte Carlo. Okay, how this works? We have now a hierarchy of certain discretizations, and instead of solving this problem, our computation model, just on one realization, we do this on multiple, on one level of discretization, we do this on multiple levels. So Giovanni also introduces this notation yesterday, so that's why I will go through this a little bit more quickly. So we're still committing the first crime. So we want to estimate the expectation of Q. We approximate this by the expectation of our quantity of interest computed on a certain finest level, which is now capital L. But now, instead of using Monte Carlo directly, we split this into this telescoping sum, and then we use a Monte Carlo approximation on every level. Okay, that's the whole idea. Super simple. And the added benefit is that now we have more degrees of freedom that we can tune, namely the different sample sizes for a Monte Carlo estimator on each level. So if we therefore look into this mean squared error setting again, we still obtain our first contribution, which is the squared bias, and the variance term. And the whole motivation is that if I manage to generate my realizations for my computation model, QL and QL minus 1, so something on a fine level and a coarse level, that are highly correlated, I would hope that the variance here gets smaller as I keep increasing, or as I keep walking downwards to my more refined hierarchy. Therefore, I should get away with fewer and fewer samples on this costly model, costly levels. That's the whole ball game. You put everything, so therefore, you put everything together. What you now want to do is you want to find the number of levels, which corresponds to identifying the finest level, and the number of samples on each level to guarantee a certain tolerance. And this has been around now for, the ideas of multi-level go back to this work by Heinrich, but let's say coined as multi-level is some work that goes back now almost 20 years, and that's this kind of standard complexity result that you would get. So we're still making our assumption that the bias is decaying at a certain rate alpha, but now on top of that we also assume that the variance of these differences additionally decay at a certain rate beta, and the cost to generate one of those coupled pairs is still inverse proportionally to the mesh size. Okay, so you put everything together, you solve this constraint optimization problem of saying, hey, I want to minimize the cost. The cost is simply the number of evaluations of my model, or the number of solves I need is NL on each level, and C as a cost for each solve. So I want to minimize the cost subject to the constraints that I want a certain error tolerance to be met. This is nice because it's explicit, right? The proof is constructive in the sense that you get formula for the number of samples and the number of levels. You plug everything in, you get an estimator, and there you go. Okay, so this was my personal introduction to notation of Multilevel Monte Carlo for UQ. But now I want to take a few minutes to kind of motivate the rest of the talk. So the first question is, if I now use Multilevel Monte Carlo, I compute this number here. Why should a practitioner trust this number? Right? It's just one value. If you're thinking about our education, let's say numeric analysis, we always thought, hey, provide an error estimate. You're doing final elements, provide an error estimate. How accurate is your solution? Sure, we have this mean squared error, but how can I report on a certain accuracy? That's the first question. There will be a second question later, but let's talk about this one a little bit. So, as I said, we should report error bars somehow. That's where I'm heading. And in a course I'm teaching at KIT on statistical simulations, we're doing the usual things, right? You talk about random variable generation, Monte Carlo method, variance deduction, Markov chain Monte Carlo, all these tools. But one of the things that are important to me that I keep telling the students, don't just give me a number of a certain Monte Carlo estimate, give me error bars. How accurate, how reliable is this number? Because units matter, right? And for Monte Carlo, everyone knows that, hey, I can construct at least some empirical error bound through confidence intervals, right? I use standard limit theorem, I have some control there. And I'm quite often surprised that I don't see people that do multilevel Monte Carlo don't report asymptotic confidence intervals for their multilevel Monte Carlo estimator. because there exists a center limit theorem. So what I'm trying to motivate is that, hey, report error bars. How reliable is your simulation? Particularly if you want to transfer to practitioners in the application, right? Now, even more importantly, if you have the center limit theorem then for this multilevel Monte Carlo estimator, and this goes back to some work which is now 10 years old, and together with Håkon we have relaxed the assumption under which the center limit theorem for the multilevel Monte Carlo estimator holds. If you have something like this, then of course you can also talk about the probability of failure criterion for this multilevel Monte Carlo estimator. But now, more importantly, the second question I want to raise is, well, we're approximating expectations so far, right? Is that really a measure for uncertainty? How do you quantify uncertainty by computing expected value? I don't think it is. I really don't think it is. Think about rolling a dice, right? Then the expected value is 3.5. How is this a realistic measure of uncertainty quantification? So that's maybe something a bit more concrete. What I'm plotting here is time series of a Markov chain, right? And let's suppose I want to take the average of, let's say, the time average of this Markov chain. It has a certain very, well, particular invariant distribution, right? But if I take the average of this Markov chain, the average will be 0. However, this chain is very seldomly visiting the state 0, right? So is really computing the expected value is a really meaningful measure for uncertainty quantification? I don't think so. Hence, in this particular example, one should certainly go beyond, and for example, one way would be to, let's also compute variances, right? See how much is the fluctuation around our mean state. But the question is, why compute expectations in this setting as a measure for uncertainty quantification in the first place? Why not look into max, medians or quantiles? Right? These kind of questions this kind of thinking I want to stimulate with this talk. So what we've done many years ago is we start to look into how can we now construct multi-level Monte Carlo estimators to approximate central moments, for example, objects of this type, right? So the distance to the piece distance to the truth, an expectation, and for p equal to this would be the variance. And then with p 3, 4, and so on, you can control quantities of interest like skewness, kurtosis. Effectively, you're controlling the behavior in the tails of more. And the easiest thing to do would be to say, hey, pool is just a polynomial, right? So binomial theorem, I can expand this in terms of this kind of raw moments, what I call them. And I could simply use multilevel Monte Carlo for each of them. Plug everything together and I get my multilevel Monte Carlo estimator for the central moment. But it's first of all, it's known that they are numerically unstable, but this would also, because it's a non-linear transformation in here, right, from its raw moments, they would be unbiased. So we went to the drawing board and we looked a little bit in the standard statistics literature, and we found the concept of an H statistic, which an H statistic in standard Monte Carlo language is precisely this unbiased estimator for a central moment. Okay, so remember, in multi-level Monte Carlo, the idea was I split in this telescoping sum, and then for every term on every level, I simply use my standard Monte Carlo estimator, which is my unbiased estimator. Okay. Here I do now the idea would be the same. I will eventually split in this telescoping sum, and now on every level I want to use this unbiased estimator. Turns out that for the central moments there exists an entire family of unbiased estimators, and this H statistics have this nice convenient feature that they are the estimators that also have minimal variance. So it seems to be promising for us. I don't dare to show the next bit because the formulas for computing this H statistics, they get lengthy. Okay, they're explicit, so you can use them explicitly. And they're oftentimes written in this power sum version here. What's important is they're explicit, and we can use them in analysis. Okay, but then the idea is, as I said before, it's very simple-minded so far. We want to approximate the p central moment. We approximate this in the first crime by the p central moment of our computable quantity of interest on the finest level. And then we are splitting this in this telescoping sum again, and now on every level we're using this H statistics, right, as an unbiased estimator for the sampling moments. And the importance is that these H statistics, they are non-linear, so what I have to be very careful about is to ensure I have correlations across levels, right, because only then I will expect to have variance. So, meaning here I cannot simply write this difference as an H statistic applied to the difference. So in my notation I had to smuggle in yet another L here, by which I mean that the random samples that I used here and here are the same, right? So therefore I get my correlation. Okay, so you look into mean squared error, and since we are really mirroring what's done for multilevel Monte Carlo, we get the same structure. Formally it is the same structure. I have to do a little of analysis, so in fact here one should maybe get a lower or equal sign, because I'm using this VLP as NL scale versus variance of this difference, but this can be shown to be of order 1. Right? Okay. Good, so now this has formally the same structure as we had for the standard estimated standard expectation. Therefore, unsurprisingly, we get, in terms of structure, literally the same complexity result. Of course, it's all now hidden in the assumptions, right? The only difference is hidden in the assumption that now we need to make some assumption on the kind of bias of a certain p central moment to be of a certain rate. The variance that we've just introduced needs to decay at a certain rate for the difference, and the cost is as before. But under those assumptions, we get the same complexity results. Of course, the constants change, and in fact, the constants depend on the on p in the p's central moment. But also, this proof is constructive, and we get explicit formulas on how we should select number of samples. Yeah, so as I said, the only difference is that now we have to estimate a different type of bias and a different type of variance. So there has been work in this direction before. For example, Alexei Chernoff and one of his former PhD students, they also introduced a multi-level Monte Carlo estimator for variances. Okay? So remember, our idea here is not necessarily to construct a variance or a p-central moment, but we want to construct it in a multi-level way. That is, it needs to satisfy a certain guaranteed error criterion. And the difference to the existing work by Alexei is that they didn't use H statistics, so they had a slightly simplified analysis at the expense of having a biased estimator, and they had to correct the bias and therefore got slightly worse complexities. But the ideas, they have been around in the literature for a while now. Okay, so I don't, so of course there is no, very seldomly there is free lunch. So for us the difficulty is we won't be using these unbiased estimators, but they have this nonlinear dependency all over the place, and this power sums. So because what we need is then actually to be practical is we had to compute these variances. This was kind of related to the variance of a certain H statistic on the final level minus the H statistic on the quarter level, right? So we need an unbiased estimator for that, in really to gain any kind of practical benefits. And I will only sketch the idea here, how we got there. The precise arguments, I will refer you to this paper, and we can talk afterwards over coffee. So the idea is that we're going to look into some other quantity of interest first, not just our quantity, but into, let's say, differences of quantity of interest and additions of quantities of interest between coarse and fine. Okay, and by doing that one now we look into this bivariance H statistics, and by it's really that constructive. By comparing coefficients in a certain polynomial ansatz, you can use this idea to construct unbiased estimators for these variances. And I mentioned before, these formulas for the H statistics, they're already cumbersome. The formulas for the unbiased estimators are ridiculous. I mean, they're explicit, it's really a tedious calculation. Okay, not this true. It got to a point where the estimator for, let's say, the fourth central moment didn't even make it the appendix of our paper because it was too long. Right? It's really ugly. It's really ugly. However, they are explicit and you could do them, and if you really want to see this formula, they are implemented in this Python library called XMC. Okay? Okay, so what can you do with those? This is a test case that we investigated. It's in aerodynamics, seems to be one of the standard test cases. We look into this airfoil and we consider now a flow around this airfoil. Right, here we are. And we consider both geometric and operational uncertainties. So we have certain uncertainties in how the geometry of this airfoil is designed, and then some operational uncertainties like the angle of attack and the Mach number. And then we let's say we use as a black box. Here's a hierarchy of the meshes that we are going to use just to sketch. They get increasingly fine. And what we want to do is we want to compute the first 4 moments. Okay? When you look into the proof, and we have done that, you see that there's a certain monotonicity in the accuracy, in the sense that if you tune this Multilevel Monte Carlo method to be accurate for, let's say, the 4th moment, this is an upper bound. It will, in the sense that it will also ensure that the 3rd moment and the 2nd moment are met by the same tolerance. Okay, so we tune everything to be satisfied for the 4th moment, and then you get pictures of this type. And the PhD student at the time, Michele, he came up with these plots, and these plots took me a long time to understand. So I will give, we have a bunch of those plots. That's why I will try to sketch a little bit what's going here. But first, what we are comparing here is the so-called quantity of interest was our pressure coefficient. At some point at this airfoil, there's a shock where the air is separating from the airfoil, and this will typically then lead to this kind of, and this profiles to this inflation of variance around this point. So in this plot, here what we're plotting is, for the case that we have both geometric and operational uncertainty, we're plotting a mean computed for this pressure profile and the plus minus standard deviation, and here importantly standard deviation are tuned, or here is tuned in a way that the variance is accurate to a certain tolerance. Okay, and then the plots on the left, we just is to indicate, hey, we looked into different cases and different quantities of interest, and we separated between the case that we only looked into geometric uncertainties, only operational, or both. And the dashed line is kind of a reference value that people use from the 60s. They have done some aerodynamics experiments. They also identified some uncertainties on certain parameters. We used them, and now combining everything together. And now the colorful lines is pretty much now using all information for these 4 first centered moments, in the sense that we're computing a mean value, we're computing some standard deviation, and now there are these triangles pointing inwards or outwards. This has to do with skewness and kurtosis, namely compared to a Gaussian, we have fatter or lighter tails. Okay? So now this information we can all extract, and just to tell you a little bit about complexity, is that the numbers are too small. So I will pick a certain relative error, let's say 1% error. If you did this, we didn't do that, but if you did this, we just extrapolated. If you did this on the hardware that we used, it would take you 2 weeks to run the same simulation for the first 4 moments. For us, it was 4 hours. Okay? So this is the type of benefit we get. And just by looking into the colors, again, numbers are not relevant. That what do I want to say? So the lowest red one is if I did single level Monte Carlo, and it's more expensive than if I just did multi-level Monte Carlo for the expected value. However, if I want to also tweak and tune the Monte Carlo in a way that ensures a certain tolerance guarantee for the variance, which is the second red curve, this is already more expensive than doing multi-level Monte Carlo for all 4 moments, right? So you get for free 2 additional moments. And then Michele went on to, in his PhD thesis at EPFL, to use these tools to design, for example, the shape of an airfoil under the constraint that it has a certain capacity for fuel. These kind of questions. Okay. To Good. But now that we have constructed some ideas of how we can go beyond expected values, one gets greedy, right? So now why not go even further? So we have started with the expectation, now we have variances, maybe skewness, kurtosis, and so on and so forth. Why not go further, in particular for targeting problem in optimization, in particular risk-averse optimization? We are kind of interested to look into quantiles, right, as an example. So, and these quantiles are a little bit tricky because I can't write them explicitly as an expectation of something. It's always given as, for example, what the representation that we're using as a variation principle or as an optimization principle. Okay, so the approach that we came up with is that we start to look into parametric expectations. So we still have our quantity of interest here, but now what we're doing is we say, hey, there's another sufficiently nice function phi given to us, or we can choose as we like. And so this function phi now depends on two variables. There's a parameter theta and our random input. And now, therefore, I can take the expectation of this one. This is some function capital phi of theta. It's a parametric expectation. So what do we have in mind? Well, the first, maybe obvious one would be to take phi simply to be the cosine of theta q plus the imaginary unit sine of theta q. Right? Because if we were able to compute this expectation, we would get the so-called characteristic function, which completely describes the entire distribution of a random variable. Okay? So this would give us, in terms of uncertainty quantification, really the full distribution of our output, not just some moments. Okay, now the way I at least think about distribution is I find it more accessible to think about PDFs or cumulative distribution functions. In that case, we could also express it in this formula by using as this little function phi here, the indicator function. Now, the indicator function is also what we're sticking with for now. However, it has a bottleneck. I mean, it's kind of convenient. It tells a story, I think, but it is discontinuous. And discontinuities, although I mean Monte Carlo is nice because it has very minimal regularity assumptions, the discontinuity is kind of a challenge if you want to do multilevel Monte Carlo, because eventually, let's say we fix a certain theta value and we simply would do then this is just an expectation, we would do multilevel Monte Carlo, you would have to estimate these type of variances, right? So the variance of phi of our quantity of interest on the phi level minus phi of quantity of interest on the course level. And because of the discontinuity, this variance will only decay very, very slowly. Right? I have to have a very fine grid to resolve the discontinuity. So there's not much gain. And this has observed in literature before, and there's now different strategies how one could remedy this one. One, maybe a little bit numeric analysis inspired, is to say, hey, if I have this step function here, why not smooth out the step? Right? So why not kind of regularize this one? Of course, I'm introducing another parameter, and I have then this account for that practice. This has been done by Mark Giles and co-workers. And also Alexei Chernov has come up with a way that was not directly designed to target this, but was say, hey, I can also approximate my CDF within the class that I can represent by a certain number of moments. And of course, then by computing moments, I know how to do this multi-level, I also get a certain, in that class, a certain estimate for my distribution. Okay, so our approach was slightly different. I can't really tell you exactly why our approach was different, but somehow it worked out. So we kind of said, okay, let's make our lives more difficult first before we hopefully make it easier. So that's why I'm suggesting you take this particular function here. Okay, so by q minus theta plus, I mean the positive part, and the reason I do that is it's now a Lipschitz continuous function. I don't have any jump, so it's nice, and I have all this nice bounds apply as before. And there is this relation between, let's say, the CDF of my quantity of interest q to this function phi, capital phi that I've defined here, to this identity here. So somehow I'm going and taking a detour. I introduce an abstract function. There is maybe some useful connection to what I'm actually interested in, let's say the CDF, but at the cost that I would now have to estimate derivatives of this function. Okay? If I want to ensure a certain accuracy on the CDF, this means I need to have control over derivatives on phi. Okay, so do I really gain something? I hope, I'm convinced we do somehow. So that's the game that we're playing. And in fact, I could differentiate another time, so I could relate the, if I have sufficient regularity in my capital phi, I can of course also extract the PDF, obviously. But now comes the interesting fact is that I can also look into minimizers of this function, and turns out that these, for example, the minimizer of this function phi is precisely the tau quantile of this distribution. And if I'm looking into the value attained at the minimum, then this is the so-called conditional value at risk, which is another risk measure that's very popular in engineering science. So this particular arbitrarily quite abstract looking function seems to carry lots of information about the quantity of interest. So we're at least for quantiles and CDF approximation, we're sticking with that. Okay, so we're Lipschitz, that's good. So now the idea is again, remember, multilevel Monte Carlo, personally I think it's very nice because it has simple ideas. So we're sticking to simple ideas, and the idea is simply saying, hey, we want to approximate this function for theta in a certain, let's say, interval. So we are simply doing some interpolation. So we take a few selected nodes in that interval, hold one theta. For each of those nodes fixed, this is just an expected value, right? And I could use now multilevel Monte Carlo estimator to estimate these selected expectations, and then we interpolate. So it's the idea, as I said, is relatively simple. And so, for example, I would get the estimates at these purple points, and then I have somehow to interpolate to get an entire function. Once I have this function, I can of course take derivatives. Right? Okay, so that's the whole idea, and what I'm sticking to in this short presentation is I will stick to spline interpolations. Okay, so we're interpolating between splines, and the whole idea really is to be efficient. Is that when I perform this multilevel Monte Carlo approximation for different values of theta, I use the same random variables that I obtained through my computational model. Okay. So there's take your favorite approximation theory books, there's some standard results on spline interpolation. You can control, for example, derivatives of spline interpolations and endpoints. Of course, you have to enforce certain regularity on the function that you want to interpolate. The interpolation operator satisfies this bound here, it has a certain cost. And very importantly, that's why I want to spend a little bit of time on the last one, which I call the inverse inequalities. In our initial complexity analysis, we had to control derivatives of our interpolator. Okay? And these are not so easy to come by for us. So for spline, we then were able to, there's this inverse inequality, what we're using is that we can relate derivatives of the interpolator to the norm of our interpolator with a factor that in front that takes care of the number of times I'm computing derivatives. Okay, that's what I call inverse inequality, because we're going from derivatives to the operator itself. Okay, so now we have to talk about what's the error criterion. And again, not the smartest choice in hindsight, but what we decided is we want to measure the error in L infinity. So now if we had to do the same stuff again, maybe we would stick to the Hilbert space. But okay, so that's sometimes you learn, hopefully. So we're working in L infinity, we're looking again. This will be our multilevel Monte Carlo estimator of the mth derivative compared with the mth derivatives of our function phi in squared L infinity term, and we take the excitation about the whole thing. That's the object we want to quantify. Okay, so we split the error into 3 terms. So we get a term that is controlling the squared interpolation error, so exact function, interpolation of the exact function. We have a term that is now what we call the squared bias, because it accounts for the discretization level L, and then there comes our statistical error because it has something to do with our multilevel Monte Carlo estimator. Okay, so same procedure as before. We're going from left to right. If we want to ensure that this whole thing is bound by a certain tolerance, then controlling the first term will fix the number of interpolation points n. Controlling the second term will then help us identify which is the finest level. And then lastly, the statistical error will help us to find how many samples we should select on each level. Okay, now, so what's going to happen is, of course, if I'm going to finer and finer accuracies or tolerances, the number of interpolation points will increase. If I use it as a long vector, this vector gets longer and longer. So therefore, to the analysis, we will embed everything in little infinity. Okay. And now it's not so clear anymore, or we have to be a bit more precise. What do we now mean by variances? Right? Variances, or now we're in the Banach space, so now we have to define this variance of this vector psi, which we define here. Good. So it's kind of the worst case variance. And then there's this very convenient, technical useful result that now if I'm looking into a variance in a sum of independent values, then this satisfies this inequality. Okay, so that's what this is what we have to use. This is variance concept here. Okay. Putting everything together, we of course first ask, okay, is there any use in that? And the complex result is that's what we get. Okay, of course we need to refine our assumptions, right? So now we're talking about parametric expectations, which are functions. So we take the worst case bias, a certain rate. We have to look into something that controls the variance eventually at a certain rate, and the causes as before. We start with just approximating, let's say, the function itself, so no derivatives. And since we're doing interpolation, we need a certain regularity of our function. Yeah. And if we do this kind of in a rather direct way, that is the complexity what we get. The second term is pretty much the same as we get for multilevel Monte Carlo up to the logarithmic factor, but we get another term here that accounts for the cost of performing an interpolation. Right? So at this stage, we want to be very precise. In hindsight, also this was very, very tedious and very hard actually. So this term is screwing us. Oh, wrong button. This term is screwing us over, right? Because it's large. However, now came the idea that maybe if we have this flexibility of doing multi-level, why not use also different type of interpolation on each level? Right? Why do we need the same kind of accuracy on interpolation on different levels? And by doing that one, you can get rid of this term here. Okay, and you get the same complex result also in that case. You get a slightly sharper result if you assume more regularity here, but I don't want to spend time on that. Okay, so now let's continue this discussion of complexity. Remember, if I want to know something about the CDF, I need to compute derivatives. So let's suppose I want to compute now m derivatives, m being larger than 1, and again, ignoring the interpolation cost, I get a complexity result that is again suffering from an additional logarithmic term, but now I also lose in the rates. Okay? So approximating derivatives is expensive. Not really surprising. Okay. And remember, we want to compute if you want to go to the CDF, quantize and conditional characteristics, we need first derivative. Same for, it's very similar for analytic functions with the additional benefit we're not suffering in the loss of rates. But they have different changes in practice. That's why I'm sticking to splines. Okay, so first example. We have seen some SDEs yesterday. We will look into this kind of very simple SDE in one dimension. We want to now take the solution, which is a model for a stock price. We compute a certain payoff, which is the quantitative interest Q, given by this formula here. And the first observation is that this is a random variable, of course, but it has a mixed distribution in the sense that it has an atom, a zero, and then a continuous part. Okay, so a mixed distribution, and we want to define its entire. So looking into the CDF would be kind of odd, right? Because it would have a jump, so we don't have regularity at all. So the only thing we can do here is maybe look into the characteristic function. The characteristic function is nice, on the other hand, because it's smooth. Right? So that's why. So here again, we look into the characteristic function. Actually, it's now the 2 function. And both functions are smooth, and we perform our estimate on this one, and we get results like this. We perform a certain discretization, in this case, Milstein scheme, some time-stepping scheme, and the reconstruction that we get is of this type, where first we have the real part, and then the imaginary part, and together it gives us the characteristic function. Okay, and you see the interpolation where we have assumed a certain regularity. The plot on the right is to indicate that, hey, the theory is kind of confirmed by the numerics here, but I want to stay on the left plot because it also indicates something that I want to spend also 5 minutes on, which is we're tweaking our method with a certain epsilon, but we're kind of extremely conservative. Right? If we actually compute the error, we're overly conservative, and that's practically it's a pity because we are wasting computation resources. And we will see some talks by David later and by Niklas tomorrow, or on Friday, I forgot, sorry Niklas, where they look into really expensive problems where you don't want to waste this level resource. Okay. Now comes a problem for, with a view on time. I'm going to skip 2 slides, but I want to still summarize something. Remember, we have this result to approximate also first derivatives up to a certain accuracy. So the question is now, in hindsight it's obvious, but if I now tweak the Multilevel Monte Carlo estimator to give me a function estimator that is accurate also for the first derivative, what can I say about the accuracy for the CDF, for the quantile, and for the conditional value at risk? Okay. And again, by some very simple modularity arguments, is that if I now tweak my Multilevel Monte Carlo estimator for this particular function here, in a way that it has a mean squared error for the first derivative that is sufficiently accurate, all of these derived quantities of interest will also meet this tolerance. Okay, that's nice. Because it's nice, now we have this kind of what I call a posteriori uncertainty quantification, right? So I tweak my method once, I get my estimate phi hat, and including phi and prime, and now in hindsight I can compute many things as often as I like. Of course, if I want to do this for different quantity of interest, so I would, let's say different quantiles, I would get different values of tau in this function here. Therefore, of course, the constant that is hidden inside this big O notation, this will change, right? So there we have to be careful. Okay, I'm skipping an example where we use this now to compute quantiles in a very simple toy fruit fly PDE, or your favorite elliptic PDE. We can talk about this later, but I want to come to a subtlety which is a practical bottleneck. So far this was all done on pen and paper code calculations, aiming towards, hey, what happens if our tolerance tends to 0, what's our complexity? But that, I mean, what we've realized when talking to people in practice is that sure, this complexity is nice, and having guarantees that the error is met, fantastic, but it needs to be useful in practice, right? You need to be able to compute numbers. And our analysis that we've done was based on what I call a priori upper bounds, and they were super conservative because of what I mentioned earlier, this inverse inequality. So the analysis that we've done was again by splitting into an interpolation error, statistical error squared, and discretization error squared, so the bias squared, and a statistical error, and then using some of our assumptions, we got to this kind of 3 terms. And these terms here come from this n minus 1 raised to a certain power, these come from this inverse inequality, and they were really screwing us over, because if the tolerance gets small, the number of interpolation points n gets large, so this factor gets really, really large, so this had to be very tiny in order to compensate for that. That's the whole thing, right? So, a little bit small possibly, but what I'm plotting here is kind of, if we use this step here to estimate these errors, we could look into interpolation error, that was really quite easy. We could look into the bias and the statistical error, and use certain error estimates. Let's focus on this one first. This is, if you do this for the first derivative, just for the bias, there should be a black line, it's somewhere in this lower bundle, and the red curve is the a priori. Okay, it's slightly conservative, right? It's slightly higher than the actual error. It's bad, but it's not too bad. If I'm going to higher order derivatives, this distance gets massive, right? So even if I want to approximate the first derivative, I'm losing 3 orders of magnitude. You can't see the numbers. But if I use this a priori bound, I'm 3 orders of magnitude too small. Of course, this is sacrificing compute time, and it gets worse for statistical errors. So the red one is the one from the a priori. There's a black line somewhere down here, and there's green and blue as well. So green and blue are kind of our empirical error estimators that we then developed to come up with sharper bounds. Okay, and this I want to at least sketch the idea very, very briefly, and I'm, let's say in the interest of time, I'm focusing now mainly on the idea of the statistical error. Okay, so I skip the one for the bias, there we'll do some smoothing using kernel length estimators, but I want to just tell you a very neat trick that the PhD student Sundar came up with to estimate the statistical error by some bootstrap argument. So what's bootstrap? If you remember from some statistics basics, you have a sample and you redraw from that sample. That's bootstrap or jackknife. Okay, now how did we use this here? Well, once we have a multilevel Monte Carlo estimator, the estimator is defined through a certain bunch of correlated samples on each level. So if I have this triangular array of samples, I can resample from that array, right? So for every level, I resample. So by doing that one, instead of just having one estimator, I can use this bootstrap idea to come up with an entire sample or ensemble of another estimators. And this I use to estimate empirical variances. So now these psi guys are really another estimators for my multilevel Monte Carlo estimators, simply by redrawing according to a certain rule. And these type of ideas really helped us to bring the statistical error, which was the red curve, if you do this a priori for the first derivative, on top of this black curve. So we really got away with much sharper error estimates. Of course, it's empirical, and we may have only asymptotic consistency, but turned out to be extremely useful in practice. And yeah, so this is then also part of this Python library XMC, where we have implemented these methods. Okay, this brings me to conclusion. I will only read the take-home message. So what I want, my whole goal for this presentation was to showcase some of the, let's say, ideas, how multilevel Monte Carlo ideas can be branched to some adjacent concepts that will eventually help you to extract more information about the quantity of interest. I also want to mention that this kind of, it's from a practical point of view, I'm convinced it's very important to come up with adaptive procedures that really adapt to the problem at hand. This asymptotic analysis, it's fantastic, it's a first step, but we should not stop there. And lastly, I want to acknowledge that I consider to be very, very lucky to have worked with many fantastic people. I could therefore I want to put a few references here with names of people that I've worked with, and with that, I thank you for your attention.